Now, if TCP flows are synchronized, the dynamics of the aggregate window, as shown in the upper part of the graph, would have the same dynamics as any individual flow. The quantities on the y-axis here would simply be different. Specifically, the number of packets occupying the buffer would be the sum of all of the TCP flows windows rather than the window of any individual flow. Now, if there are only a small number of flows in the network, then these flows may tend to stay synchronized, and the aggregate dynamics might mimic the dynamics of any single flow, as shown. But as the network supports an increasingly large number of flows, these individual TCP flows become desynchronized. So instead of all of the flows lining up with a sawtooth as shown in the bottom part, individual flows might see peaks at different times. As a result, instead of seeing a huge sawtooth that's the sum of a bunch of synchronized flows, the aggregate instead might look quite a bit more smooth as a result of the individual flows being desynchronized. And we can represent this sum, which is the buffer occupancy, as a random variable. At any given time, it's going to take a particular range of values. The range of values that this buffer occupancy takes can actually be analyzed in terms of the central limit theorem. The central limit theorem tells us that the more variables that we have, and in this case, the number of variables are the number of unique congestion windows of flows that we have, the narrower the Gaussian will be. In this case, the Gaussian is the fluctuation of the sum of all of the congestion windows. In fact, the width decreases as 1 over root n, where n is the number of unique congestion windows of flows that we have. And therefore, instead of the required buffering needing to be 2t times c, we can get away with much less buffering, in particular 2 times c divided by the square root of n, where n is the number of flows passing through the router.